we have now completed Book 4, and we're going to embark on Book 5. And with Book 5, we're going to do something different. We're going to talk about planets, which we have pretty much completely put to the side up until now, until we actually had the tools to ask the right questions. And so Book 5, in terms of the website, begins with a review of the Mysterium Cosmographicum. And what I'm going to do before we get to that, I'm going to review a little bit from the beginning of the new astronomy, because you didn't have the opportunity to work through the new astronomy, which came before the Harmonices Mundi. So in the course of some of the material that we cover in Book 5, I'm going to have to reference some of the ideas that are developed in the new astronomy so that it makes sense. And so what I wanted to do, this is the introduction of the new astronomy, which just starts from the idea of what is it that we see? What are our sense perceptions telling us? And what can we and can we not conclude from that? So, Star, you want to start reading? We'll just jump in and go through some of this.
You need the light out?
Yeah.
Yeah.
Chapter 1. The testimony of the ages confirms that the motions of the planets are orbicular. It is an immediate presumption of reason, reflected in experience, that their gyrations are perfect circles. For among figures, it is circles, and among bodies, the heavens, that are considered the most perfect. However, when experience is seen to teach something different to those who pay careful attention, namely, that the planets deviate from a simple circular path, it gives rise to a powerful sense of wonder, which at length drives men to look into causes.
So that's from the new astronomy and is the basis for his whole investigation of that book.
Now, orbicular, it means from circular orbit, it means?
Well, I'm not sure exactly. It probably, orbicular probably just means that it's a closed path.
Mm-hmm.
So that doesn't, he then says it's an immediate presumption of reason, right? And this goes back to Cusa and other influences in terms of why a circle is this perfect shape, and why that should be the path which the planets actually follow. Mm-hmm. And I'm not sure if we'll go into it tonight or not, but we will go into the different models which could be developed based on that idea of the perfection of circular orbits, and trying to make the observation somehow fit into that assumption. But as Kepler develops his theory, and as he acquires, well, even the existing data before he gets a hold of Tycho Brahe definitely shows that the path itself is not a circle. There are ways of trying to describe it in terms of circles, but he already knows it's not a circle, and if it's not going to follow that path, then the question is why? What could cause it, as opposed to simply trying to describe it?
Will we be going through that as to how you know that it's not a circle?
Yes. So, okay, so continue reading a little more.
The starry ball. Our Earth, which we are standing on, is the huge blue sphere, and the blue circle around it is the horizon, the limits of our sight. Imagine you are on your back, looking up. This is a live view of the night sky from an undisclosed location. Watch it carefully.
Okay. So this is the Earth, and this would be our horizon. So this could be any night that you go outside and look up at the sky. So what do you see?
Mars.
Well, see something.
You see the things that are above the horizon. You do not see the things that are below the horizon.
That's correct. And this is also what Richard was referring to the other day in terms of this snapshot, right? You see a picture of the sky, and it seems pretty static. Okay, so scroll down. Okay. Fred?
Oh, sorry.
Go ahead.
Actually, this picture doesn't move at all. Oh, that's what stargazing is like. You don't see a particular star move any more than you see the hour hand on a watch moving, yet the change happens. Let's say you look up again in an hour. Here's what you see.
Okay.
It moved.
It did?
It doesn't hardly look
Well,
like
go
it.
back.
Okay. Go. All right. Yeah. Go back up.
I'm a little confused.
Yeah.
I'm not more than confused.
Okay.
All right, if you're lying on your back
Yeah.
and the Earth is the blue sphere,
Yeah.
Earth is very
Oh yeah, the red dot is
and the
moon.
horizon, I mean, if you're looking up at that,
Yeah.
you don't see the Earth. I don't understand that.
Yeah. I don't know. Maybe their description of lying on your back and looking up at this is
Or you see
really.
a semi-sphere.
This is more if you were out in space, looking at the Earth, I think,
I think so.
and
It's
watching.
like you were God.
Yeah, that's not what I would see. I'll show you some pictures in a minute. So go back up.
It has moved, but it's unless you're watching it continually, you wouldn't notice it.
Well,
The two dots at the top of this thing are
Mars,
above.
yeah.
Mars.
If you want
Definitely
Mars
to
has changed.
think of, you have a red dot. You've got these three
And the
pretty
two-
much in a
two in the
row.
middle.
That's Orion's belt.
And then you've got this group. You've got this group over here that's more or less straight up. And now go to the second one.
Some of them are below the circle.
Yeah, there were three before. One seems to have disappeared, and the vertical line before I think was about here. So this seems to have moved over in this direction, and one of this group of three has disappeared,
Does that mean below the
went
horizon?
Below the horizon, yeah.
or it exploded. One of them. We don't really know.
That's right.
Okay, so what change have we observed?
It's very little, but if you're out there laying on your back for that hour, you would notice it.
Okay, all right, now go down to the next one. This is something a little later.
Yep.
So this red dot is way over here, and this grouping, which had been up here originally, has moved over this far.
And the dots are now below the horizon. You wouldn't be able to see them.
Yeah,
because they're
maybe
under
that's one of the original three.
Right, but it's right on the horizon, which would be hard to see.
Yeah. Okay. So the stars all seem to move in the sky, doing this for an entire night, until the sun comes up and ruins your view. You observe this, noting one particularly bright reddish star that stands out to you. Okay, so go down to the next one.
There it
Okay.
is.
Now this is if you look during an entire night, and the yellow, this would represent sunset when the, okay, so the sun just went down,
Right.
which allows us to see anything.
Then it comes up, yeah.
Okay, now, okay, so what can we say now? If we now, and remember, this motion only occurs in the mind's eye.
Right.
You don't see that, but your mind can sort of synthesize all these snapshots to say, well, what's the process that's generating these particular views?
Why do they make the moon stationary? Because the moon's not moving at all.
I
Where's
wasn't
the
sure
moon?
that that was the
This-
moon.
this
I was
is-
just going to
this
say.
is that's supposed to be us.
No, no, no.
Right to the left there.
No,
Oh, that?
I was going to
Yeah.
say they're all
It's kind of
rotating
big.
around that.
Well, we don't know what that is. It looks too small to be the moon, but you're right. You do see. Now these stars
Could be a North Star.
seem to be rotating around this one, which isn't moving. What about all the others? Are they rotating around it as well?
Yes.
Yeah.
Seem to be.
So it'd be the North Star.
Well, what does that mean?
Because the polar star doesn't
Well, it
seem to
means
move in the
that-
night sky.
The north is over there.
You know, it's like if you look at the Big Dipper or whatever it is, the Big Beaver or whatever, the Big Bear, you know, it moves around. It seems to orbit around the North Star. The North Star seems to stay in place, and the Big Dipper seems to spin around it over the night sky.
Mm-hmm.
But for whatever reason, because it's over the North Pole, so you're looking, it's not moving as far as your eye is concerned.
Okay, now are all the stars moving at the same speed?
Roughly.
No. The ones on the outside are
Yeah,
rotating
compare,
faster.
look at some of these,
Compared to the inside.
compared, say, to these.
Yeah.
Gives you a equatorial kind of idea. A sphere.
Now, I want to, see if I can, let's see. Oh, I know, I think they're down here. They're down here. I can get my, This is a time-lapse photograph that would be relatively short. And you can see, so that each individual star would trace out these short arcs. And one thing that I would point out, I mean, there's two things. It's not a real high-resolution picture, so it's kind of grainy. But you can see what we saw on the animation, where there seems to be a center to this circle, that things are not moving in straight lines, but it's actually a circle.
Right.
And the other thing that I would point out is if you look at, say, a particular group, that the left, let's assume that the left-hand edge of the line is the starting position of the star, and the right hand is the ending position, that a group of stars is moving together, right? Is that clear from the
Yeah.
picture?
Right.
So that you get a sense of an overall motion of the entire sky. And that over a period of time of observations, you could make a map, and you could measure, you know, using a sextant or something, you could measure angles between all of these stars that over days and weeks and months and years always seem to be constant. So that this is where this idea of a celestial sphere would develop, where these bright points of light seems to have a fixed position on this revolving sphere that surrounds the Earth.
Well, is it the sphere that's revolving, or is it the Earth? I mean,
Well, you don't know. at this
Well,
point.
that's, see, rather than, you know, when people say, oh yeah, well that's the North Star, is think of it from the standpoint of discovery. This is what you see, what you make of it, how you explain it. That's the whole issue of hypothesis. And I mean, since we're obviously not moving, right?
Well, you're just lying.
Huh? Yeah,
You're just lying there on your
right.
back.
You're laying on your back, mind your own business, and you're watching all these bright lights revolve around you. So it would be very easy to come to the conclusion that we are in the center of the universe, right? We're it. We're at the center of the universe, and everything revolves around us.
Except for the pole stuff.
Well, and that's another question. Why would that star not move?
Stubborn?
It's stubborn. It's extra heavy.
That's where God lives.
It's glued.
It's glued. Yeah. There's a thumbtack there. Those are all the kind of questions that would come up. And I have a couple other pictures. Oh, let's see, man, this is.
You can shoot your
First, I
arrows.
just gotta. Let's see. I can't tell what my next
Right
one
there.
is. Yeah, but okay. Well, okay. All right. That's.
You gotta zoom in.
Yeah. This is a longer exposure. And I now where's the North Star? Where's that point that's not moving?
What's the time lapse? Do you remember?
Well, this is obviously quite long.
Yeah.
I don't know. You can't really see a complete line.
Well, I've never seen that.
Yeah, I particularly like this one. I've got another one. Let me see if I can. Oh yeah, I can see.
You know, it's also odd about it. It seems that on the left, northwest corner, so to speak, it seems to be bowed in a certain direction.
Yes.
But down in the other corners.
Yeah. Now that's another one.
And a satellite.
Huh?
And a satellite or an aircraft.
Yeah, that's probably an airplane. The red line that goes on and off. That must be an airplane. But now where's the North Star?
Right in the middle.
Well, it's not right in the middle.
It
Almost
has
in
its
the
own
middle.
orbit.
Right, that the North Star actually does move.
Right.
This would be the closest thing to a fixed point in the sky. And you can see if you were to measure any of these lines, you know, that's about a quarter of a revolution.
Well, how do you know that's the North Star from that picture? What if it's the
Well,
South Star? The
Well-
South Pole?
Because there is, well,
As we live up here, we don't get pictures of the South Pole.
Okay.
well, you don't know.
Not from that.
If you traveled, and this is again an interesting thing, if you travel on the Earth, this picture will change.
Right.
Where you see this apparent center of rotation is going to change,
How about-
which will tell you a great deal about where you are
Right.
on the Earth.
How about the equator? Can you see the North Star at the equator or the polar star?
Well, the picture that I just showed you,
Oh, yeah, that's from the equator. That's
Now-
why they're moving in two different directions.
yeah, this would presumably be closer to the equator,
Huh.
because you can clearly see there's curvature here, and you could estimate where the center of that circle is.
Right.
And you could do the same thing to estimate where the center of that circle is.
Fascinating.
It's hyperbolic.
So that while everything seems to be revolving in a circle, that depending on where you are on the Earth, you'll see that in different ways. You might see what we've called the North Star, or that relatively stationary star. Maybe you'll see it directly overhead. Maybe you'll see it somewhere, at 45 degrees. That's more or less what we would see. And in other parts of the sky, like this, you know, I don't know which one would be the North Star, but it's going to be much lower in the sky. And if you were directly on the equator, what would you see?
Straight, vertical.
But what? I mean, what
Line.
would be straight and vertical at the equator? I'm not sure.
Lines.
No, you'd still, because you'd be looking both north and south of the equator, so you
That's why you
would
had
see
the
something
two.
like that, yeah.
Well, these lines would be vertical.
Not all of them though, would they?
Well, these would be vertical. Everything would be going around like that, and when you get, it would still be going. It would be going vertically over a very small circle.
Yeah, but you have the Earth on the axis too.
Well, and that's what defines. Well, let me put it this way. How do we know there's an axis to the Earth?
Because there's no middle point in the North Star.
Well, but see, these are all assumptions or hypotheses
Right.
that someone had to discover to try to explain what they were seeing. Because it's not obvious. It doesn't have to be that way. Maybe we're stationary, and the sky, if the sky is a sphere that's rotating, it has to rotate around some axis. It could be sort of, you know, random, but that's not what we see. From any given location on the Earth, we see the same repeating circular motion of virtually everything in the sky.
Yeah, but that changes through the seasons. Because,
Well,
like you said, the axis of the Earth and the movement of the Earth.
Actually, no, that doesn't. What you
Changes the
can
sky.
what you can see in the sky changes,
Right.
but the sky is not changing, and the Earth is not pointing in a different direction. There are all kinds of paradoxes that come up in this that you may think you know,
Yeah.
but aren't quite what you think.
I was going to say on that the first pictures we looked at where they said that you know, they had the Mars, but if you had like 2 or 3 planets, what would be obvious if you were laying on your back at night and you could see several planets is that the planets are rotating on the same plane, the ecliptic.
Okay,
Where
well,
the
hold on,
stars aren't.
hold on. Let's not get ahead of ourselves.
All right.
First, because this is the most obvious motion that you're going to see.
But unless you're Leonardo or unless you're on drugs, you're not going to actually see that.
Well, I mean, if
You would,
if you spend time
So you're not going to be laying
outside,
on your back all night out and looking at the stars.
if you spend time outside, you will see certain groups of stars that are low in the horizon, and later on they're going to be high, right? So you can infer that it moved from there to there within a couple hours. And if you were actually studying it, you could draw a little picture of that. And you could maybe you don't sit and stare at the same star all night, but you can draw conclusions that it did move in a continuous way from there over to here, and then it either went below the horizon and we couldn't see it anymore, or the sun came up and the whole sky was too bright to see anything. And that's actually what happens in terms of the seasons, is that the part of the sky that you can see when the sun is down changes, but it's not that the Earth is pointing in a different direction. So it's interesting to actually, the only way to really do this stuff effectively is to make little models so that you can actually see what's happening. But this motion is referred to as the first inequality. the first change that we see in this apparently fixed vault of stars is everything seems to rotate on a daily basis.
So the first inequality is that
Good.
everything rotates?
Yes, is this daily rotation of everything. And everything seems to rotate together, so that the relations between individual stars do not change. Okay? Now, if I can, this screen is so bright when it's, uh-oh. All right, now I want to go back. Okay. Now I want to go back to this. Okay. So what we have now is we have this rotating vault of stars. Fred, you want to?
Do certain stars move faster than others? It seems that each star moves in its own particular circle, and there seems to be a spot where the star doesn't move at all. This spot that doesn't seem to move during the night, but around which the other stars move, acts like the end of a large pole. So we can call the star located there the pole star. Now we have some directions. It also seems that the sun rises and sets not in the pole direction or opposite it, but in between its direction and the opposite. We can name these directions. The pole star direction is north, unless you're in Australia and see a certain cross that seems to rotate while maintaining the same position, and call this the pole south. Its opposite is south, and the directions of the rising and setting of the sun, east and west respectively.
Okay, so we can use this, we can use the sky to define our directions on Earth. So that if you pointed in the sky to that point that seems to be stationary, that's how we define north. There's magnetic north, but this would just be geographical north, I guess. And 180 degrees in the opposite direction would be south. And the sun would seem to rise and set halfway in between, which would be east and west, rising in the east and setting in the west.
What's the Southern Cross?
Well, if you go into the southern hemisphere, there is no star that is stationary.
Mm-hmm.
There's kind of an empty spot. So you can't identify a star like that.
Right.
You would have to look at a certain grouping of stars that seems to be moving around a spot.
That's the way.
Huh?
Around that hole.
Yeah.
That's it.
So that's how you would determine what south was, even if there's nothing there to point to.
Mm-hmm.
Okay. So okay. So go down again. So that's the first inequality, or first motion.
First
Okay.
and second motions. Around a dozen or so days later, you see the moon every night as well. Let's take a few nights and spend them watching the sky. Though you may find it easier to look at two at once to compare them, how would you do so without a computer animation? The motion would only be in your mind, or expressed by your mind in a drawing.
Okay, so this is one particular night. Where the moon seems to be carrying out the same daily motion as all of the stars. Okay, let's go down and we're going to look at another night. Now try to keep this picture in your mind. We also have that little red dot going around.
Okay, everybody have this memorized?
Oh.
All right, now,
Can I minimize, can I reduce the
try,
size, do you think?
try that.
Yeah, you can see the difference, the arc.
Can you reduce the brightness of the screen? It gets a little...
Well, we have to get Ryan to put my screensaver back on. This
Yes,
is like
I know.
blinding.
It's outrageous.
I'm gonna have to get.
Oh, on your side.
Yeah.
The white screen is
Yeah,
kind
which
of
will
blinding in the dark.
Washington's Crossing got obliterated.
Oh,
There
You can
somewhere.
put that back on.
I know you can, but I don't know how to.
I just have
You
to
know.
find it, yeah. Okay, well, if, I don't know, can we, okay.
Yeah.
So, all right, so here are 2 nights.
Move back a little bit.
And the second one, the arc seems to be tighter, but it takes longer for the moon to,
well, the sun also sets in a different spot.
yeah.
Oh, no, it's actually, it's
The
kind
moon
of the
seems to
same.
rise higher, but it arcs down to the
Straight.
horizon faster
Oh,
than it
yeah,
does
right.
on the first one.
And the moon isn't setting at the same time each night, right?
Right.
This night, it's setting a little bit later.
Right. And it looks like it's rising a little bit higher, too.
Now, and what about the red dot?
It's setting later.
It's further advanced here also, right?
Right.
I think so, isn't
No.
it? There
No,
it's up?
not.
I don't think so.
It's back.
About the same?
About the same.
Okay, so that's about the same from one night to the next.
It is a bit more advanced.
But the moon definitely seems, it's hard to tell, but in terms of its relationship to the other stars it's with, that's kind of tough.
Ooh. It's almost
it's-
identical.
Yeah, but it definitely,
It's farther down.
well, this one sets before that one.
Right.
Yeah.
But it also arcs higher, it seems to stay,
Well, partly this is a 2-dimensional rendering of a
Right.
sphere, so it's a little hard to judge that. Okay, go down to the next one. I think there's another night. That's too far. Let's see. Yeah.
Oh, last night, okay.
Yeah, so compare those two. Okay. Okay.
Sun comes up later.
So
And the
now
moon
it's,
comes up later.
it's substantially further behind. Well, no, well, there's not too much difference
It comes
between
up earlier,
those.
he said.
yeah.
What about the red dot?
Comes up earlier in the last night, sets about the same. No? Sets earlier.
Much later.
Rises, sets.
So the moon, one thing that I think we can say is the moon has an independent motion.
From the others.
From, yeah. If you sort of define a star as one of these fixed points of light,
We weren't sure about that.
that there are other objects in the sky that, while they do sort of partake of this daily motion, there's another motion on top of that, which is actually in the opposite direction.
How do you know that?
Well, if you were to look at each of these, if you were to take,
Well, you don't know it from looking at these particular images, but you would know it over time. You would see certain objects surpass others, or other objects would appear to go backwards.
It seems that the moon is going around with the rest of them. It doesn't seem to be going.
Well, actually,
well, it does on any given night.
Then where's the opposite?
It's
Where's
coming
the
up,
thing?
it's coming up sooner. Well, that seems out of sync. What's going on?
Yeah, I'm not sure that these are running.
Yeah.
They're not running in sync.
Right.
So they're getting sort of out of whack. But go down because I think the next,
Okay,
I think there's a paragraph to read. Okay, let's read this. And Sheila, can you read that?
What did you discover? How high was the moon in the sky at sundown on the 3 days? Among which stars is it found? Does everything in the sky move at the same speed? Which moves faster, the stars or the moon? You have now discovered the difference between the first motion and the second motion. The first motion presenting itself to the mind of all the stars, including the moon, and the second motion seen only through thought and comparison of the particular heavenly bodies moving against the stars. The first motion is that of the whole heaven and of all its stars from east past the mention to the west.
Meridian.
Oh, meridian. Okay, sorry. The second motion are those of the individual planets from the west to the east.
Okay. So, just so that's clear. The first motion is what seems to be everything going around from east to west, rising in the east, going overhead, and setting in the west. That's what the sun does, that's what the stars do. But then there's a second motion, or what would be called the second inequality, is there's a separate motion which causes certain of these objects to lag behind, if you will, this daily rotation of the sky. So that relative to the stars, to this fixed vault of stars, these other planets, or the word planet means wanderer. So there are certain objects which seem to move in the opposite direction, but at a slower rate, so that every day they do still go from east to west, but they've moved a little bit relative to those stars each day.
And you're not just talking the motion or the apparent motion of Mars going backwards.
Well, what do you mean? What? The apparent motion of
Mars seeming to go backwards and then...
I don't know what you're talking about.
Okay.
Okay? All I know is everything seems to be going around me.
Right.
But then there are a handful of these stars or objects, whatever they might be,
Right.
that over time move in the opposite direction.
Or don't move as fast, one or the other. You could
I mean, you
interpret
could-
it
They
both
lag
ways.
behind, I think is the
Yeah. They lag behind. They don't come up as quickly, and from overnight or weeks, you know, they move relative to the background of stars.
Okay, but they're not going literally in the other direction.
No.
You
We're not
could
saying that.
see it,
Well,
no, but you could look at it
We're not
both ways.
saying that
If you were
yet.
just lying on your back, you could, in your mind, you could interpret it as either way. You could either look at it as being lagging back or moving back. I mean, it would all be perception. It would be how you perceive it.
Right.
Yeah. See, when you say, well, what are they really doing? That is a very difficult question to answer.
Okay, but I'm just trying to get it straight in my mind that you're saying it's not appearing that they're going counter to each other.
Well,
Lagging, I mean, I can deal with the word lagging.
okay. You could say, I mean,
But if
again,
you were
this all
living in
depends on
700
what
and
you
looking at it, you could
determine.
interpret that differently.
Yeah, what you determine is the actual motion occurring.
Uh-huh.
Is the entire universe revolving around me?
Yeah, no, okay, I'm with you.
Right? If so, then they're also revolving around me, but a little bit slower.
Mhm.
If that's not what's actually occurring, then maybe they are really moving in the other direction, literally. So this is all up for grabs.
Okay.
Okay, so go down far enough so we can see the picture. Then they're gonna. Sheila, just read that too.
Taking more care in the observations, it is noticed that the sun too moves more slowly than the stars. The stars are more advanced at each sunset. Here are a week's worth of sunsets as they appear to the animating mind, not the eyes.
Okay, so the idea is this is sunset, what the sky looks like at sunset. So the sun is basically stationary for each of these pictures. So relative to the background of stars, the sun is also moving in the opposite direction.
Those stars are stopping all of a sudden, moving back and then coming back again.
It's because it's a loop. The animation is 7 nights of sunsets,
Oh,
and then it starts over again.
oh, it's all.
So it's just looping.
Nice.
So, but look here, there are stars that you could see on one night and are moving below the horizon or below the sun, so that the sun is also moving relative to the background of stars. In the opposite direction of the daily rotation that we see. And also, if you look over here at the red dot, is if this is the same time, or this is sunset every day, the red dot, this is only over the course of a week, the red dot seems pretty much to be moving along with the stars. So the moon and the sun we can see most immediately as having some kind of independent motion. Okay, now let me...
The moon and the sun? Or
Yeah.
the red
Yeah.
dot and the sun?
The moon and the sun.
Okay. Yeah.
Okay, oh yeah, and this quote underneath, Sheila?
The first
This
And-
first.
This first adumbration of astronomy explains no causes, but consists solely of the experience of the eyes, extremely slowly acquired.
Okay.
Okay, adumbration. What is adumbration?
Lynn used it for a while.
Words, right?
The first hazy image, the
First
first
hazy.
idea coming from out of focus into focus. Shadow.
Okay.
Does that make sense?
Yep.
Okay.
Kind of goes along with purblind.
Okay.
Now, I mean, it's worth remembering that the giant of astronomy from about 400 AD, I guess, right? Ptolemy?
Yeah, earlier. About
200?
one or 200.
All right, 200 AD up until 1600, where we are now, was Ptolemy, which had the Earth at the center, and this was the giant of, you know, volume after volume after volume of astronomy. So from 200 AD up to 1600 AD, and then you have Copernicus, who has some approximation of the sun being at the center, and then Tycho Brahe, who has a mixture of the two.
Huh.
And so that's the scientific world into which Kepler is intervening. And each of these figures, Tycho, Ptolemy, and Copernicus, had very strong evidence for their picture. So in working this through, you have to have a bit of humility that, what do you know?
They all had exactly the same evidence, in fact.
But wasn't
It's-
that dictated by religion at that time? Because the church thought that the sun was at the center, I mean, the earth.
Well, I mean, there certainly are reasons why that would tend to remain, you know, the dominant theory. There's no question that, you know, there are quotations from the Bible that talk about this that were used to, quote unquote, prove that the earth was standing still. And all of our personal experience tells us that the earth is standing still. And so there are lots of reasons why some of these things today that we would say, man, that is really whack. But you know, this was scientific knowledge for over 1,000 years, and it's not, you know, I think it's more a testimony to people's belief in sense certainty than to just say, oh, well, it's dictated by religion. Because yeah, that is a factor, but what, you know, but what would be the evidence for anything else? Maybe that's a good way to put it. Since sense perception tells us that we're not moving, why would you fight that, right? So all of those things added together, and as we will see, if all you're interested in doing is describing the appearance, one's as good as another. So it's almost like, well, why bother? Why, you know, when Copernicus said, no, the sun is stationary and the earth is revolving around it, well, you see exactly the same thing. It's almost, what's the point? What have you actually accomplished by introducing a new theory?
How did they explain a comet at that time?
Well, that was actually a problem, because you could explain it as something which was an effect of the Earth's atmosphere, because part of the idea was that you had once you sort of concluded that you did have these planets that were also revolving around the Earth, the idea, you know, going back to Ptolemy, was that you had essentially glass spheres around the Earth, and these planets were embedded in these glass spheres, and they all turned one inside the other in perfect circular motion.
Nested spheres. A little one, then a big one, then a big one, then a big one.
So a comet couldn't cut through those. So it would have to be something that basically occurred just in the Earth's atmosphere. That's how they'd have to explain it.
Now those spheres go back, that's Aristotle.
I'm not certain that, I think that's right. There was a whole, you know, sort of doctrine that developed around this, that the Earth was at the center because it was really sort of the pits. Things fell down because that's where they wanted to be. That the heavens were completely different.
It was certainly a religion all by itself, even if it wasn't religion per se.
Yeah, it was.
Because it was accepted without question.
It was Manichaeism in the sense that the Earth was the dregs of matter.
Yeah.
And the heavens were the spiritual world.
Right. And that there was no connection whatsoever. There was no way of using, for example, experiments on Earth to tell us anything about the heavens. They were ethereal. They were, you know, heavenly. They were of another world. And there was really no way to know them. Okay, go down a little further. Okay. Done?
At the same time of year, while the red star rises near sunset and is particularly bright, do other stars change their brightness during the year? We can observe it at its peak around the middle of the night. By using our mind to remove the daily motion of the heavens, we can focus our powers of reason upon the single star's second motion. This brings out more problems. Let's combine a couple of weeks of observations, creating the following animation in our minds.
Okay. So I think that's where it just started.
Starting over.
So it moves to the right, then up and to the left. I'm sorry, to the left, and now it's moving to the right and down. And now Now it's going backwards.
Uh-oh.
That's it. That's where it starts.
Oh.
So it goes to the left. And then to the right, much
Bobbing
more
and
quickly.
weaving. It's like a good boxer.
Yeah, much more quickly. And then it stops and
truck
starts
driver.
moving to the right again.
Right.
Okay, and I'm going to show you a couple pictures.
And this must have really created a lot of problems for these guys that were trying to explain all this.
Oh,
The wanderer.
okay.
Get this one thing there in the universe that just kind of wanders around on its own.
Now I got to drag. Let's see, I think I need to drag the whole thing over there. Let's see. Drag this over there. So once you have, once you sort of have your mental map of the stars, is you can then try to measure the motion of these wanderers relative to that background. So this would be, that's October 13th, December 21st.
What's the one in here?
Somewhere in between. It's not dated. So viewed from the Earth, looking out from the Earth against this background of stars, Mars would be seen to move in that direction. So that would be, let's see now, I can't tell.
Is that, yeah.
I can't tell what's what. Okay. Now this is, now these are photographs. This is looking at the same place in the sky over a series of many nights where, and I'm not sure what the directions are here, but this would be the observed motion of Mars, where while all the stars are moving in a nice circle, right? Those were perfect circles. These other objects not only have independent motion, but have motion like this. So they stop and change directions. And at another time, it might look like this.
Is this is Mars, right?
This is still Mars, yes.
And the others don't do this, do they?
No.
Yeah, actually,
Not as
retrograde.
obvious.
The retrograde motion?
it's not as obvious, but yes.
It's conspiracy time.
So the other one, let me try to compare them. Right, it's an open, it doesn't loop over itself. So this would be seen to occur at certain times of the year, but from 1 year or over many years' observation, the loop itself changes. So what the heck is going on here? This, for perfect heavenly motion, this is pretty strange. Okay, let me just see what else I have on here. This is the Farnese Atlas, which I think is around 200 AD. It's a Roman copy of something that may be a star atlas that Hipparchus put together in 200 BC, 1 to 200 BC. That's not certain, but this is the oldest picture of Kepler I know of. This is when he got married, which was, I think, 1576. He's about 25, 27 years old, just after the Mysterium was published. Let me just see if there's anything I left out. Okay, so that's it for my pictures. Now, so I can get rid of this. So these are all the problems in terms of the observations that any astronomer would have to address. Okay, let's see what's below this. Okay, and this just traces out now that obviously is not on a circle. So you would, if you're going to try to explain that kind of motion, you're going to have to come up with a little more complicated mechanism than a perfect circle, perfect uniform motion. Clearly that is not the case. And these planets like Mars, sometimes they look brighter than they do at other times, which could mean that they're, oh, I know, there was another picture I wanted to, let me
You
see.
can
if-
also read this quote. I think it'd be good. Read this little paragraph.
Okay.
Who's next on the reading list?
Margaret?
This bright star, which, like the sun, usually was slower than the stars, being left behind them every night in the westward motion, reaches a time of staying even with them, and then, contrary to its usual motion, moves faster to the west than the fixed stars, before again stopping and resuming its eastward motion. This, is that quote there?
Yes.
Yeah, that's from
Okay.
Kepler.
Gives this,
Gives rise to a powerful sense of wonder, which at length drives men to look into causes.
Now, it is remarkable that it took an awfully long time before anybody seemed interested in looking into causes.
Like how long?
Well, like until Kepler.
From,
Well, Ptolemy's like 1 or maybe 200, well, it's like 1 or 200 AD. He writes the Almagest, which has detailed observations and charts and all of that, and describes the motion of the planets. And for up until, let's say, 1500 with Copernicus, that up until that time, that this was sufficiently accurate to predict where the planets were going to be and what they were going to do. And Copernicus, while he made an important change, I mean, certainly this retrograde motion is one of the most compelling reasons to change your basic view of the heavens, because this is so strange. But Copernicus didn't ask about causes either. Copernicus is just saying, I have a simpler way of explaining, in particular, this motion.
and he did all that stuff with the little suborbits that did while it was.
Yeah, I mean that went on before Copernicus, these epicycles, and we'll get into some of those things.
No, but step back for a second. Kepler says the observation of these discrepancies in what you would presume that the most perfect of motion is circular. I mean, you see that in the array of a flower in a plant. You drop a pebble in a pond, and you see circles. The examples abound. Clearly, there's evidence of non-circular motion in the most beautiful of the heavens. So Kepler, this mind, says, well, this evidence of non-circular, seemingly irregular motion gives rise to a powerful sense of wonder, which at length drives men to look into causes. So what does he mean by causes? What's this causes business?
The cause of the motion. You can't see it.
You have to understand a higher principle which subsumes the seeming contradiction.
Now Kepler in the harmonies, in the title of the harmonies, he refers to his origination of celestial physics. And so part of Kepler's conceptual revolution is that he begins an exploration of the physical causes of the relations among the heavenly bodies. That just the way on Earth you would figure out the physical interactions between something that floats called a boat, and what it floats in called water, and you'd have to know the relationship between that which floats, a boat, and that which surrounds the floating boat, and what the boat would do wrong to make it not float and sink. This is a question of physical causes. So what part of Kepler's revolution is, he says that the motions of the universe as a whole is susceptible to being understood from the standpoint of physical causes.
Did he ever explain the anomalies in their orbits?
Oh yes.
Yeah, that's what he refers to as the new astronomy, or that's the name of the book that they're talking about here, the new astronomy, which is significantly before the harmonies. Even let it roll around in your mind. Even the idea that there's a physical cause of the physical relationship between the sun and the planets, and there's a physical relation, the way between iron filings and a magnet. You would understand that there's a physical relation there. There's something about the magnet, and there's something about those iron filings.
Now, this physical relationship, did he call that gravity?
Yes, in fact he did. As Fred asked last week, was it known that the moon was the pull of the moon was the cause of the tides? In this new astronomy, Kepler hypothesizes that specifically. And again, this is 80 years before Newton. So it's not that obvious that you would ask, what is the cause? You might just say, well, what do the gods ordain the relations be? And there are no physical causes. It's just what is. And it's certainly not susceptible to the activity of the human mind, called reason, because it's the heavens, which are unknowable by mere man.
We certainly can't go there. We just see them as dots, dots in the sky among other dots in the sky.
Well, I mean, just all this thousands of years of discoveries about the heavens without even going there. And then we actually developed the technology to go up there, and Obama shuts it down. It's unbelievable.
Excuse me. I had some other pictures there.
Yeah, I want to see where that red dot is going.
Not the
Do you
Loomies.
see the whole
Okay.
orbit?
Now this,
Sets every night. It happens once every 2 years.
oh, that's nice. Okay. Now, now this is a picture. This is taken from behind the moon. Okay, this is not a picture that you could see from the Earth.
This is our moon.
This is our moon, yeah. That would be the sun over there.
Oh, that's the moon.
This is Mercury, Mars, and Saturn.
Well, where's the light coming from to the right of the moon?
It's the sun. That's
No,
the
no,
sun.
no. He says to the
Right.
other
must be.
Oh, I don't
of
know.
the Earth.
Oh, yeah, it must
Maybe,
be the
yeah,
reflection.
maybe it is. Yeah, it's not. That's not
What,
clear.
this is a satellite picture?
Yeah, this is a satellite. A satellite going around the moon took this snapshot.
I'd like to get a copy of that. That's cool.
And what this shows you is that these wandering objects, including the sun, the moon, and I mean what we would call Mercury, Mars, or Mercury, Venus, Mars, Jupiter, and Saturn. Right? Those are the visible planets. They all seem to move within a certain band within this background of stars. And that's what became known as the ecliptic. And this is one of the best pictures I've ever seen of that. That gives you a sense of there being sort of a plane through which all these planets move. Now we know them to be at greatly different distances. If this is Mercury and that's Saturn,
What are the three? It's Mercury.
Distance.
yeah, it's Mercury, Mars. I think it might be Venus. I forget whether it's Mercury, Mars, and Saturn. I think that's what it is.
Saturn's usually oblong.
A reddish glow, though?
Huh?
Doesn't Mars put off a reddish glow?
Yeah. Yeah, I
Saturn's
don't know
usually
exactly.
sort of oval in the sky.
I don't know exactly why they look the way they do. But it gives you that sense. That's the ecliptic. And that's where this whole notion of the zodiac comes from. That the zodiac are the stars or the patterns of stars that all of these planets move through. I had showed you before this picture. Castor and Pollux are these two, equally bright stars. That's what's called the
Gemini.
constellation Gemini. This is Cancer, which is not so obvious an asterism, and this is Leo. So that all of the so-called signs of the zodiac are simply the groupings of stars which these wandering planets move through during the course of years on end. They never go, like Orion, right? Orion is a well-known constellation. The planets are never seen in the constellation Orion. They go through, 12 groupings of stars, which is, completely arbitrary, and that's where the zodiac comes from. That's what sort of makes them special groupings of stars, because they're visited by the planets.
I think it originated with the Rig Veda, right? The original zodiac.
That I don't know.
Was what?
You said the Rig Veda.
I'm sure there's a lot of that in different cultures.
And this is just a picture of, if you were to put this on a sphere, that you could, I guess it's the red path. Those would be the groupings of stars that the
Equinox,
planets.
that would be
What, the
the plane
ecliptic?
of the equinox.
The ecliptic, you mean?
Yeah, the ecliptic.
Yeah, that would be the ecliptic, because this is a theory that the Earth revolves around the sun. Okay, so I don't want to impose this idea on you, but if this were the case, then the idea is you would see from the Earth if you had your star map, right? If this is midnight in this direction, then you would say, well, the star, if we could see the stars during the daytime, that the sun would be here, right? You have to be able to create this whole sphere because you can't actually see the stars. But if you knew that at midnight you're seeing these stars, then it must mean that the sun on the opposite side of the Earth would be relative to that background. And you could do the same thing for all of the planets. Okay? So I think that's all I want to do on those. Oh. Okay. All right, so let's go down and see what. Okay. Ryan, you want to read here?
Sure. Retrograde, a paradox. It was apparent that the three superior planets, Saturn, Jupiter, and Mars.
Superior meaning they're further away from the sun than the Earth. And one way you would know that is that Mercury and Venus never get very far from the sun in the sky. Like you would never see Venus or Mercury high in the sky at midnight. They were all relatively close companions of the sun, particularly Mercury. It's very hard to observe Mercury. The only time you have a chance to see Mercury is right before sunset or just before sunrise, so it's always very close to the sun.
So it was apparent that the three superior planets, Saturn, Jupiter, and Mars, attune their motion to their proximity to the sun. For when the sun approaches them, they move forward and are swifter than usual, and when the sun comes to the sign opposite the planets, they retrace with crab-like steps the road they have just covered.
Okay, so that's this retrograde motion. And all of the superior planets do exhibit this retrograde motion. Mars is the most obvious.
Want me to continue?
Yeah.
That this retrogression or backwards motion occurs always when the sun is opposite these planets, wanderers in Greek, is peculiar, for they do not make their path through the stars in the same time as the sun. Our bright red star Mars, for example, moves through the stars and regains its original position in a little less than 2 years, although the exact amount of time changes from cycle to cycle, owing to the influence of its proximity to the sun on its path. These two different but interacting tendencies among the second motion of a particular planet are known as the first inequality, its motion through the stars, and the second inequality, the relationship of its proximity to the sun on its motion. In order to study the first inequality by itself, we'll have to remove the influence of the second inequality.
So you have all these interacting motions, which is what that make the appearances not only complicated, but talk about shadows on the wall of the cave. I mean, if you assume that the Earth moves, and you don't know what the motion of the Earth is, then what can you possibly determine is the motion of other planets that you're observing from that moving Earth? right? If I'm moving in an unknown motion and trying to determine the motion of Mars, let's say, how can I possibly figure that out? I can't go to Mars and look back at the Earth. All I have are these directions in the sky. I don't know distance.
Well, could you look at like Mercury and Venus to get an idea, because you can kind of see the way they're moving, and maybe make an assumption that Mars moves that way and the Earth moves that way.
Well, I mean, that certainly had been done, but Kepler is going way beyond sort of, you know, general description.
Yeah.
He's not only trying to precisely determine their orbits, but using that well, we're not using that, but using a principle, a cause, to determine what must be determining the motion that we see. And the observations then become a way of testing a hypothesis. But the appearances themselves don't tell you that. They don't give you the causes from what you see. Because even if you say, you know, the Earth is moving as opposed to stationary, that does help you sort of resolve this, you know, this particular problem. It still says nothing about the cause of the motion. Why aren't they perfectly circular and uniform? Uniform in distance, uniform in speed. Why aren't they that way? And if they aren't that way, why are they this way rather than another way?
How many years does it take Mars to orbit the Sun?
It's only, it's a couple of years.
Okay.
A little less.
Want me to finish the paragraph?
Yeah.
But in order to separate the second inequality from this first one, they could proceed no otherwise than by considering the planets on those nights at whose beginning they rise while the sun is setting.
That would mean they're
Correct.
at exact opposites. They're just coming up as the sun is going down, so they would be on opposite sides of the Earth.
Which thence were called achronikoi, or night rising. At the very moments of conjunction with and opposition to the sun, they are traversing their own true and proper positions. But since they cannot be seen when in conjunction with the sun, only the opposition to the sun remains as suitable for this purpose.
So one of the things that Kepler recognized in terms of how do you try to sort out all these different motions, including our own, is that there are certain kinds of observations that give you sort of a unique insight or unique information. If the assumption is that the sun is at the center and you're trying to determine the actual motion of a planet independent of the Earth, that if I could line up, if I saw the planet directly behind the sun, then I could say, okay, it has that position, that direction from the sun. It's going to be the same as my observed, you know, its observed position from me. That I can say, okay, at that instant, if I were on the sun, I would see it in exactly the same place in the sky, right? Regardless of the motion of the Earth, because we're in a line. But since you can't see it when it's on the other side of the sun, the only way that you can create the same line is when it's at opposition. When the Earth is in between the sun and the planet. But the same thing would apply. That if I see it over there, that's exactly where the sun would see it. Is that clear?
Does everybody get that? Maybe
Yeah.
you want to draw it on the board.
Yeah.
If the sun, if you were standing on the
Someone
sun,
hit the lights, please.
you would see the same Mars in the same position with regard to the fixed stars that you see from the Earth.
If that's the sun, and that's Earth, and this is Mars, yeah, I'm going to see Mars relative to some background of stars. And I know that if I were on the sun, I would see Mars in the same place.
Same place as
I would see it in the same
the star.
position. Right. I'm the only thing
That
that
the
I
sun
can
would see.
The only thing that I can see is how Mars is moving relative to this, what seems to be a fixed background of stars, right? That rotates every day without changing. So that's the only information I have. And I can say from one night to the next that Mars seemed to move like that relative to me. But one of his important ideas is if the sun is in the center, and if it is somehow the source of the motion as it is for light and heat, that then what I really need to know is what is the motion of Mars relative to the sun. And how can I do that if I'm moving on some unknown path myself? Because obviously my path, you know, if you saw my head, you know, relative to the blackboard, right? And I move like this, you'll see my head change in terms of where you see it on the blackboard. But if I'm moving like this, you won't see any change in where you see my head. And if you don't know where I am moving, if I'm taking some strange looping path, that will completely, or if you're moving as well, right? If we're both moving at the same time in the same direction, different directions, that means that the observation that you're making against this background of stars becomes really confusing. So he tries to find these sort of unique points of observation where he can eliminate the motion of the Earth and say on such and such a night, I could say that viewed from the sun, that's where Mars was. And if you could collect enough of those kind of oppositions, where maybe some other time Earth is here and Mars is there, right? And you can collect enough of those, you can start to create an idea of the independent motion of Mars, even though you never left Earth.
I think that's what Lynn, or maybe Einstein, says that is like the most brilliant insight that Kepler had. That was because it also assumes the hypothesis and then uses the assumption to actually verify the assumption.
I mean, Kepler has to develop just one after another of these assumptions, which he obviously has to somehow test and confirm. But for example, there's another, if he can determine that there's a certain point in Mars orbit that it returns to on a regular basis, then he can look back at what the Earth is doing. That in particular, I think, is the one that,
Is that the one? Okay.
yeah,
I'm confused.
where he basically, you can create series of relationships between any of these observations. And if he can, one of the things that he does is he determines that Mars returns to the same point in its orbit on a regular basis. And so then he can use that as a fixed point to look back and determine the motion of the Earth. So he can then refine how the the observations taken from this moving Earth have affected the apparent motion of Mars.
And the sun, for that matter.
Yeah. So that there are all of these kind of insights that he has to make to try to both understand what the actual motion is, and then figure out what physical principle could possibly explain that. But it's sort of, you know, there's just, in the new astronomy, he goes through one idea after another, most of which don't work. But he tells you, well, I tried this, and then I tried 6 other ways of trying to look at this problem, and none of those work, so I thought I'd try, you know, I got to take a different approach, and so I did 12 of these, and, you know, so it's just this endless pushing for a breakout. You know, I was thinking, when Jerry Rose was up in New Jersey this week, he was telling, he had just finished reading Washington Irving's biography of Washington, The Life of George Washington. And he says that, you know, after having spent years in defensive flanking maneuvers to keep the army alive, that at the point that the French Navy had been able to escape the British blockade, that Washington recognized that it was a moment where victory was possible, and that was the Battle of Yorktown, where he deployed the entire colonial army, basically risked everything to, you know, to attack Yorktown from land, and the French Navy prevented the British Navy from rescuing them. And he recognized, he, in spite of having spent years sort of in the trenches trying to figure out how to avoid getting captured and crushed, that he was constantly looking for the breakouts, and that you know, that's the mind of a leader. And Jerry was obviously making the point in terms of our organizing. We often get very under it in terms of, you know, fighting battles that we lose, and okay, now we're gonna try Glass-Steagall, and, you know, is that you always have to have this conception of we're going to fight for the breakthrough. We're going to, you know, and that you don't know where that's going to come. And that's equally true of, you know, the scientific mind, of trying to tackle a problem, particularly a tough problem, that most other people have just said really isn't worth the effort. That he just kept, he knew that this was knowable, that the laws of the universe and the laws of his mind were created by the same creator, and that this causality must be reflected in a knowable way, if he could just figure out where to look. And that's what, you know, drove him on this lifelong quest to find and elaborate that.